We are in section 6.2, real applications of normal distributions. The first example says the reading speeds of 6th grade students is approximately normal with a mean speed of 125 words per minute and a standard deviation of 24 words per minute. So underline that it says approximately normal. That's our key there to knowing that we're dealing with a normal distribution. Part A says, what is the probability that a randomly selected 6th grade student reads less than 100 words per minute? And again, it's talking about probability, which is talking about the area under that normal curve. So to start this problem off, let's sketch a normal curve. So our normal curve is going to have a mean of 125. So we're going to go ahead and put 125 in the middle. And since part A is asking for students that read less than 100 words per minute, 100 would be over on the left side, and less than would be shading this to the left. So we are going to find the probability that x is less than 100. And so on our calculator, we're going to use normal CDF. We're going to go to second vars and go down to normal CDF. Our lower bound is going to be negative 1 E, which is second, comma, and then 99. And our upper bound is going to be 100. Our mean for this problem is 125. And our standard deviation is 24. Select paste. And again, if you have the older style calculator, that would be what you would type in and enter. And we get our probability. And we get an answer of 0.1488 on our calculator. So again, the probability that a student reads less than 100 words per minute is going to be 0.1488. Okay, part B says, what is the probability that a randomly selected 6th grade student reads more than 140 words per minute? So again, we're going to go ahead and sketch our normal curve, and then we'll use the calculator to calculate that probability. So our normal curve still has a mean of 125. So put that in the middle. But this time the problem is asking for what is the probability that the student reads more than 140 words per minute. So 140 is larger than our mean, and more than means we're going to be shading it to the right. So the probability that that student reads more than 140 words per minute. Again, using our calculator, we go second vars to normal CDF. This time we have our lower bound, which is going to be 140. We have our upper bound, which is going to be 1 E, which is second, comma, 99. And then our mean and our standard deviation are 125 and 24 still. Paste. This is again what you would type in if you had the older style calculator. And then you get your probability. And from the calculator, we get that this is equal to 0.2660. So the probability that a student reads more than 140 words per minute is equal to 0.2660. Okay, the problem continues on to the next page, where part C says, what is the probability that a randomly selected 6th grade student reads between 110 and 130 words per minute? So again, sketching our normal curve, putting our mean of 125 on there. And that mean is in the middle. And this is saying that they read between 110 and 130 words per minute. So putting on 110 and 130. And between will be shading in between those two values. And so the probability that the student reads between 110 and 130 words per minute. We use our calculator. We go second, vars, and our lower bound for normal CDF is going to be 110. Our upper bound is going to be 130. And our mean and our standard deviation are still the same. Paste. And we get our probability from the calculator. And on the calculator, we get 0.3165. So again, the probability that a student reads between 110 words per minute and 130 words per minute is 0.1365. Part D says, would it be significantly high for a 6th grade student to read more than 200 words per minute? And then it asks for us to explain why. So again, we're going to go ahead and sketch our bell-shaped curve, our normal curve. And we're going to put in our mean, which is 125. And more than 200 words per minute, so 200 would be far to the right of that mean, and more than shading to the right. And so we're going to see if the probability that a student reads more than 200 words per minute is significantly high. And in order to do this, we're going to calculate that probability. We're going to go second, vars, to normal CDF. Our lower bound here is 200. Our upper bound is going to be 1E, which is second, comma, 99. Our mean is 125, and our standard deviation is 24. Select paste. And be careful, there is an E in the answer. That is our probability. So the probability that we got on our calculator is going to be 8.89 times 10 to the negative 4th. And so if you were to move your decimal place, your decimal point 4 places, we would get 0.000889, which is going to round 4 decimal places to 0.0009. And so this is a very, very, very small probability. And remember, significantly low and significantly high, those cutoffs were if the probability was less than 0.05. So is this significantly high? The answer is going to be yes. Why? Is because the probability that x is greater than 200, so that reading more than 200 words per minute, is less than 0.05. So the next example says the U.S. Air Force requires that pilots have heights between 64 inches and 77 inches. Heights of men are normally distributed with a mean equal to 68.6 inches and a standard deviation of 2.8 inches. What percentage of men meet the height requirement? So again, let's go ahead and draw our normal curve, since it does say it's a normal distribution. And it tells us that the average height for men is going to be 68.6. So I'll put that in the middle. It says what percentage of men meet the height requirement? And the height requirement, it says up in the problem, is between 64 and 77 inches. So putting on 64 and 77 inches. So the probability that this man is between 64 and 77 inches, and between, again, is going to be between those two values that we have, We're going to use our calculator for this. And from the calculator, we get the probability that x is between 64 and 77 is equal to 0.9484. And it does ask for what percentage. So to figure out the percentage, we're going to move our decimal twice to the right, and we get 94.84%. So 94%, almost 95% of men meet that height requirement for the U.S. Air Force for pilots. Part B says if the Air Force height requirements are changed to exclude, so we're going to exclude the tallest 2.5% of men and the shortest 2.5% of men, what are the new height requirements? So again, let's go ahead and sketch our bell-shaped curve, our normal curve. The average height for men is still the same, so let's go ahead and put in 68.6 in the middle. And the tallest 2.5%, so this would be 0.025, writing that as a decimal. And then the shortest 2.5%, which would be on the left side of this, is 0.025. And so we have to figure out this height, which we will call x1, and the tallest height, which we will call x2. So we need to calculate x1, and we also need to calculate x2. And so since we are going backwards on these, this would be using inverse norm on our calculator. And when we use inverse norm on our calculator, we have to have the area to the left of the value, which is nice for x1. However, for x2, the area to the left of x2, and we'll go ahead and draw some different kind of lines in here with a different color, is going to be all of this area. So all of this area to the left of x2 is going to be equal to 1 minus 0.025, which is equal to 0.975. So using inverse norm, let's calculate both x1 and x2. For part B, we are going to go to second vars, down to inverse norm, select enter. The area for the shortest man is going to have an area to the left of 0.025. The mean is 68.6. and a standard deviation of 2.8, and select paste. And this is the height for the shortest man. For the tallest man cutoff, we're going to go to second vars, inverse norm again, and the only thing that's going to change is the area to the left of this value is going to be 0.975, and again paste, select enter. And this is the height for the tallest man. Also notice that the step at the very top on the calculator screen is for part A if you are stuck on that one. So the value of x1, and I'm going to round that 2 decimal places, is going to be 63.11 inches. And the height for x2 is going to be 74.09 inches. So if this was the new height requirements, the pilot would have to be between 63.11 inches and 74.09 inches. So in chapter 4, we learned that probabilities can be used to determine whether values are significantly high or significantly low. And this is what we looked at in the previous example. Significantly high values and significantly low values are where the probability is less than or equal to 0.05. We have another example after this that I'm going to go ahead and circle, and we will work on that together in class. And then we get into section 6.3, which is sampling distribution and estimators. We now consider the concept of sampling distribution of a statistic instead of working with values from the original population. We want to focus on values of the statistic, such as a single sample proportion or a sample mean obtained from the population. The idea is when samples of the same size are taken from the same population, the following two properties apply. So sample proportions tend to be normally distributed, and the mean of a sample proportion is the same as the population mean. Sampling distributions of a statistic, such as a sample proportion or a sample mean, is the distribution of all values of the statistic when all possible samples of the same size n are taken from the same population. So the sampling distribution of the sample proportion is the distribution of a sample proportion or the distribution of the variable p hat with all samples having the same sample size n taken from the same population. So some notation ideas here is going to be that p is equal to the population proportion and p hat is the sample proportion like we saw earlier. Behavior of the sample proportion. First thing is the distribution of the sample proportion tends to be approximately normally distributed. And 2, the sample proportions target the value of the population proportion in the sense that the mean of all the sample proportions p hat is equal to the population proportion p. The expected value of the sample proportion is equal to the population proportion. And then we have the sampling distribution of the sample mean. And this is the distribution of all possible sample means or the distribution of the variable x bar with all samples having the same sample size n taken from the same population. So notation for this is going to be mu is our population mean and x bar is our sample mean, again like we saw earlier in the semester. Behavior of the sample mean. First thing is the distribution of the sample mean tends to be normally distributed, and the distribution tends to become closer to normal as the sample size increases. And 2, the sample mean targets the value of the population mean. The expected value of the sample mean is equal to the population mean. So 6.3 is kind of the introduction to that. This is section 6.4, the central limit theorem. In the previous section, we saw that the sampling distribution of the sample mean tends to be normally distributed as the sample size increases. Given any population with any distribution, uniform, skewed, etc., the distribution of a sample mean x bar can be approximated by a normal distribution when the sample size is large enough. And when we say large enough is going to be n, our sample size is greater than 30. Central limit theorem. Regardless of the shape of the underlying population, the sampling distribution of x bar becomes approximately normal as the sample size n increases. If n is greater than 30, the sampling distribution x bar can be approximated by a normal distribution with mean mu and a standard deviation sigma divided by the square root of n. So very important there. The more skewed the distribution of the population is, the larger the sample size needed to invoke the central limit theorem. So there's some pictures here of different histograms, and you will see as the histogram of the size, our sample size is increasing. The distribution tends to be more normal. And so if you look at A, the initial graph of this histogram is very skewed, right? But as we increase our sample size and collecting more data, that distribution tends to be more approximately normal. So the central limit theorem and the sampling distribution of x bar says suppose that a simple random sample of size n is drawn from a population with a mean mu and a standard deviation sigma. If the population has a normal distribution, or if n is greater than 30, then the sampling distribution of x bar has a mean and a standard deviation that are given here. So star those. So the mean of all values of x bar, so mu of x bar is equal to mu. And the standard deviation of all values of x bar is sigma x bar is equal to the standard deviation sigma divided by the square root of n. This is also called the standard error of the mean. And then it says if the original population is not normally distributed, or if n is less than or equal to 30, so smaller, then the distribution of x bar cannot be approximated well by a normal distribution, and the methods discussed above cannot be used. We have an example, and then right below this it says based on the test of the Chevy Cobalt, engineers have found that miles per gallon in highway driving are normally distributed with a mean of 32 miles per gallon and a standard deviation of 3.5 miles per gallon. What is the probability that a randomly selected cobalt gets more than 34 miles to a gallon? So what is the probability that a randomly selected cobalt gets more than 34 miles to a gallon? This is nothing different than what we did previously. So I'm going to go ahead and draw my bell-shaped curve, my normal curve here, and we are going to put our mean on, and then look at exactly what this problem is asking. So the mean for the Chevy Cobalts, it says we have 32 miles per gallon, so put 32 on here, and it's asking for more than 34, so put 34 on, and more than means we're going to be shading to the right. So in order to calculate the probability that X is greater than 34, we are going to go to second, VARS, normal CDF, and our lower bound is going to be 34. Our upper bound is going to be 1E. Remember, E is second, comma, 99. Our mean is going to be 32, and our standard deviation is 3.5. Select paste, hit enter one more time, and this is going to give you the probability. And from the calculator, we get that that probability is equal to 0.2839. So the probability that a randomly selected cobalt gets more than 34 miles per gallon is going to be 0.2839. So part B on the next page says 10 cobalts are randomly selected and the miles per gallon for each car are recorded. What is the probability that the mean miles per gallon exceed 34 miles per gallon? So I want you guys to take a second and look at the difference between part A and part B. I want you guys to notice there's a few differences here. First of all, this one is only asking about A randomly, which is just one randomly selected car, whereas part B says 10. So we have we're sampling 10. The other difference is that this is asking about what is the probability that a randomly selected cobalt gets more than 34 miles per gallon in part A, whereas B is asking about the mean miles per gallon. So we are sampling that mean, or our X bar. And so for this problem, again, same idea, but instead of having our problem as being the probability of X, we actually are sampling X bar, and that's going to be greater than 34. And since we're talking about X bar, this means that our mean of X bar is still equal to the mean that we have in the original problem, which is 32. But our standard deviation of X bar is equal to the standard deviation divided by the square root of n. So we have 3.5 divided by the square root of n, and n is our sample size, which is 10. So again, as we do this and we use normal CDF, we plug these both in for our mean and for our standard deviation. We're going to go to second, VARS, down to normal CDF, select enter. Your lower bound is going to be 34. Your upper is going to be 1E99. Your mean is still 32. However, our standard deviation is now going to become 3.5 divided by the square root of our sample size, and for this one it is 10. And then go down to paste, select enter, and then we get an answer for our probability. And from the calculator, we get the probability that X bar is greater than 34 is equal to 0.0354. So again, this is the probability that the mean miles per gallon exceeds 34 miles per gallon for those 10 cars. Part C now says 20 cobalts. So this time we have 20. So think about how this is going to change our problem. And it says, are randomly selected and the miles per gallon for each car are recorded. What is the probability that the mean miles per gallon exceed 34 miles per gallon? And would this result be significantly high? So first thing let's calculate is the probability that X bar is going to exceed 34 miles per gallon. And again, we would have our mean, and I'll write that underneath. The mean of X bar is still going to be equal to 32, but our standard deviation of X bar is going to be equal to sigma divided by the square root of n, which is going to be 3.5 divided by the square root of, and this time we have 20, our sample size increased. And I'm going ahead and using our calculator. We're going to go seconds, vars, down to normal CDF. Our lower is 34, our upper is 1E99. Mean is still the same, and the only thing that's going to change on our standard deviation is now that our sample size is 20. Go down to paste, select enter. We get an answer of 0.0053. So the second question for this problem says, would it be significantly high? And the answer is yes. And the reason why is because the probability that X bar is greater than 34 is really small. And meaning really small means that it is less than 0.05. So the next thing says the rare events rule for inferential statistics. If under a given assumption the probability of a particular observed event is very small, then the observed event occurs significantly less than or significantly greater than what we typically expect. With that assumption, we conclude that the assumption is probably not correct. So the next example that we have, I'm going to go ahead and circle and we'll look at that one together. And right below there is a summary to kind of look at. I'll leave that for you guys to look at on your own. And then we have section 6.5, which is assessing normality. So it says, in this section we present criteria for determining whether the requirement of a normal distribution is satisfied. The criteria involved is a visual inspection of a histogram to see if it's roughly bell-shaped, identifying any outliers, and constructing a normal quantile plot. So we saw normal quantile plots earlier this semester. So the first thing is a normal quantile plot, or a normal probability plot, is a graph of points x, y, where each x value is from the original set of sample data and each y value is the corresponding z-score that is expected from the standard normal distribution. So procedure for determining whether it is reasonable to assume that sample data are from a population having a normal distribution. First thing that we are going to do is we are going to create a histogram. So this is back from a previous chapter. And we want this to be roughly bell-shaped. So histogram, so we're going to say roughly bell-shaped. Next thing that we're going to do is we're going to check for outliers. And in order to do that, you guys remember you do your 5-number summary, get your fences, and see if we have any outliers. And the way that the book words it is that it's okay if we have one outlier. So we're going to go ahead and say no more than one outlier. So any more than that, then it's not considered normal. And also if the histogram is very skewed to the right or very skewed to the left or uniform or something along those lines, then we would say it's also not normal. The last thing that we're going to check is the normal quantile plot. And it says the population distribution is normal if the pattern of the points is reasonably close to a straight line. And the points do not show some systematic pattern that is not a straight line pattern. So not normal distribution here says the population is not normal if either or both of the two conditions apply. First, the points do not lie reasonably close to a straight line on the normal quantile plot. And two, the points show some kind of systematic pattern that is not a straight line on the normal quantile plot. So there's an example right below. And it says a random sample of 100 adult males. Blood pressure was recorded. The data then was used to create a histogram and normal quantile plot given below. Determine whether the data appears to be from a population with a normal distribution. Explain why or why not. So we have to go ahead and check those three things. So the first one is going to be the histogram. So is the histogram roughly bell-shaped? I would say yes, that looks like it's roughly bell-shaped. You can see the histogram on there. So we'll put down histogram, roughly bell-shaped. The second thing is, do we have any outliers? We don't have a data set here to look at exactly. However, if you look at your histogram, you'll remember that outliers would be far off, meaning that you would have another bar maybe way over here or way out here, something along those lines to where it's not close to the rest of the data values, and that's what an outlier is. So this is going to appear that there's no outliers. So we'll say no outliers. Again, we would need more information. We would actually need the data values to check that more accurately. And then the last thing is to check that your normal quantile plot, which is over here on the right, is approximately a straight line. And if you notice and you look at all those points, yes, they are. So we'll say that the normal quantile plot is approximately a straight line. And because of this, we can say that this is coming from a population that is normally distributed. So we'll say therefore, so 3 dots again, therefore the population is normally distributed.